Hello everyone, myself Dr. Rajesh, working as an assistant professor in the Department of Chemistry, JSS Arts, Science and Commerce College, Gokak, which is affiliated to Rani Chennamma University, Belagavi. Well, in the last few videos, I have discussed about the crystal field theory with reference to octahedral complexes. That means how the d orbitals are going to split in octahedral complexes, and the crystal field stabilization energy calculation and determination of delta naught I have discussed in the last 6 videos. Now in this video I will discuss about the crystal field theory with reference to tetrahedral field or tetrahedral complex. So that means how the 5 d orbitals, what we call this one as a degenerate d orbitals present in the central metal ion, are going to split into different sets of orbital in presence of tetrahedral field or in presence of in a tetrahedral complex, because 4 ligands around the central metal ion will not produce a spherical field. So therefore degeneracy will be lifted and the 5 d orbitals are going to split into different sets of orbital having different energy. So that is the meaning, or that is the concept of this heading, that means crystal field theory with reference to tetrahedral complex. So in order to know the tetrahedral field or the tetrahedral arrangement of ligands around the central metal ion, it is necessary to know the or realize the how it looks like. So for that, let us consider one tetrahedral complex where the central metal ion is surrounded by 4 ligands, 4 ligands in a tetrahedral fashion with an angle of 109 degree 28 minutes. So now if I insert or if I drop this tetrahedral arrangement in this simple cube, how it looks like? It looks like this one. So that means when you drop this tetrahedral complex in a simple cube, so it looks like this one. So that means metal will come exactly at the center of the cube and ligands will come exactly at the alternate corners of the cube. That means 4 ligands will occupy alternate corners of the cube. Here another 4 corners will be empty. So this is the structure, that means this is the arrangement of tetrahedral arrangement of ligand around the central metal ion. When it is compared with the simple cube, in a simple cube the metal will come exactly at the center of the cube and ligands will come exactly at the alternate corners of the cube as shown in this figure. Now in order to know the position of the d orbitals which are present on the central metal ion, so it is necessary to know about the position of x, y, z axis in a simple cube. That means we have to first compare the x, y, z axis with respect to simple cube. So that means if I take this x, y, z axis concept, that means x, y, z axis, this system, if I drop in this simple cube, so that means if I insert or if I drop this x, y, z axis in this simple cube, how it looks like? It looks like this one. So that means x, y and z axis will exactly passing through the center of the face of the cube. Here you can see the center of the face of the cube here. So that means the direction of, see the directions of x, y, z axis are pointing to the center of the faces of the cube. So if I insert, if I drop the x, y, z axis in this cube, what will happen? The x axis will come exactly at the center of the face of the cube and y axis will exactly pass through the center of the cube, and similarly the z axis will exactly pass through exactly at the center of the cube here. So now we know that when we insert the tetrahedral complex in a simple cube, it will looks like this one. So that means metal will come exactly at the center and the ligands will come at the 4 alternate corners. And if I drop if I insert the x, y, z axis in a simple cube, the directions of x, y, z axis are pointing to the center of the faces of the cube. Now if I mix these two, that means if I insert both x, y, z axis and this tetrahedral complex simultaneously, how it looks like? It looks like this one. So that means the same ligands will come here. So this will be the metal and these are the ligands. So this is the exact structure. This is the exact structure what we have to write in exam. That means if they ask you exam explain the crystal pill splitting with reference to tetrahedral complex, you have to write this diagram. That means figure 1, this diagram you have to write. So that means in order to explain crystal pill theory with reference to tetrahedral complex, we can compare the regular tetrahedron. That means a regular tetrahedron is related or compared with a simple cube. So for this, let us consider a tetrahedral complex which is placed in a simple cube as shown in the figure 1. So that means let us consider a tetrahedral complex present in a simple cube as shown in this figure 1. Here the metal is exactly at the center of the cube and ligands, 4 ligands are occupying the alternate corners of the cube. Further, the directions of x, y, z axis are pointing to the center of the face of the cube, x, y, z axis. So this we can easily realize by taking this 3-dimensional 3D arrangement. See, if this is the simple cube, okay, this is the simple cube and these are the x, y and z axis, okay, and ligands are coming at the alternate corners of the cube like this one. This one is ligand, second, third and fourth ligand will come here. So that means in a simple cube, if you consider the tetrahedral complex in a simple cube, how it looks like? In a tetrahedral complex which is present in a simple cube, a metal is exactly present at the center of the cube and ligands are at the alternate corners of the cube. Here 4 corners are empty. Further, the direction of x, y and z axis are pointing towards the center of the faces. Just see here, the x axis is exactly passing through the center of this face and y axis is exactly passing through the center of this face of the cube. Similarly, the z axis is also passing exactly at the center of the face of this cube. So this is how the arrangement of ligands in a tetrahedral arrangement. Now, in order to know the position of each lobe of the d orbitals, it is necessary to compare each d orbitals with respect to simple cube. So that means I will take each, for example, T2G orbitals. T2G orbitals are dxy, dyz and dxz orbitals are there. Okay, dxy, dyz, dxz orbitals are T2G orbitals, whereas dx square minus y square and dz square are the EG orbitals. Now if I take the dxy orbital and if I insert in this cube, how it looks like? It looks like this one. So that means d, if it is x, it is y, because already we know from the shapes and orientation of d orbitals, it is clear that the T2G orbit lobes are lying in between the axis, whereas EG orbit lobes are exactly lying along the axis. This is the main fact we have studied from the shapes and orientation of d orbitals. Now since the T2G orbit lobes are exactly in between the axis, now what is the position of these T2G orbit lobes in this simple cube? Where the position of the T2G orbitals will come here in the simple cube? So in order to know that one, let us see this one. See, I will consider first dxy orbital. Okay, dxy orbital I will take and I will insert in this simple cube. So it looks like this one. That means since the T2G orbit lobes are exactly in between the axis, that means this is x axis, this is y axis. Therefore, the dxy, T2G dxy orbit lobe will come here. See, exactly it will come here at the center of the edge of the cube. Similarly, at the center of the edge of the cube here, dxy will come here, this lobe will come here. Okay, exactly here and here. Now, if you take the dyz orbital, if it is x axis, y axis and if it is z axis, so definitely the dxy orbital looks like this one. So first lobe will come here, it will touch here and another will touch here, and further it will looks like this one. Another lobe will touch at this corner at the edge of this cube and another one here. Okay, it looks like this one. So that means dxy orbital lobes are exactly touching these lobes, this edges of the cube, whereas dxy orbital lobes are exactly touching the or exactly passing through the center of the edge of this cube. Similarly, if you consider dxz orbital, so they are going to exactly point towards or exactly pass through the center of the edges of the cube in this fashion. So that means here if you consider dxz orbital, if it is a x-axis, y-axis and z-axis, the lobes will come here exactly. T to G orbital lobe will come here. Okay. So therefore, when you compare the lobes of the or direction of lobes of the T to G orbitals in a simple cube, the T to G orbit lobes will exactly point or exactly pass through the center of the edge of the cube. For example, any orbital, T to G orbital if you take, they will come exactly here at the edge of the cube. Here it will come here, T to G orbital. One more lobe will come here, or it will come here, or it will come here, or sometimes some other lobes will come here. That means T to G orbit lobes are always present at the center of the edge of the simple cube. This is one fact. Another fact is, we know that the EG orbit lobes are lying along the axis. This is the fact which we have understood from the shapes and orientation of d orbitals. Now, if this is the case, what about the position of EG orbit lobes in a simple cube? That means when we compare the lobe of the EG orbital with respect to simple cube, how it looks like. Already we know that EG orbit lobes are exactly lying along the x-axis, y-axis and in case of dz, z-axis. That means lobes are exactly lying along x-axis, y-axis means if you consider EG orbitals are dx square minus y square and dz square. If you consider the first one, dx square minus y square orbital, how the lobes are looking in simple cube? They are exactly passing or exactly coming to the center of the face of the cube, because x, y, z axis are exactly passing through the center of the face of the cube. So therefore, EG orbit lobes are also lying along the axis. Therefore, EG orbit lobes will also come along the axis. That means indirectly we can say that EG orbit lobes are exactly pointing to the towards the center of the face, and T to G orbit lobes are exactly pointing to the center of the edge of the cube. Okay. Similarly, if you take the dz square orbital, for example, if you take this one dx square minus y square orbital, the lobes will come exactly here and exactly opposite to here, and one more exactly here, and another one will come here. So that means dx square minus y square orbital, if you compare with the simple cube, the lobes will come exactly along the x-axis and y-axis. Further, if you consider the dz square orbital, so it is a z direction, z-axis. Therefore, the lobe will come exactly at this center, and here also downward side it will come here. So therefore, by comparing the orientation of d orbitals, with a regular cube, it is clear that EG orbit lobes are pointing exactly at the center of the face of the cube, whereas T to G orbit lobes are exactly pointing towards the center of the edge of the cube. Okay. Therefore, by comparing the orientation of d orbitals with a regular cube, it is clear that the direction of approach of ligands does not coincide exactly with either T to G or EG orbital. So that means when you compare the orientation of d orbital lobes in a simple cube, it is very clear that either T to G orbital lobes or EG orbital lobes are not exactly coinciding with the direction of the ligands. So that means both T to G orbital and EG orbitals are away from the direction of the ligand. So that, for example, so that means, say in this structure you can see here. See, here EG orbital lobes will come, x, y, z axis, EG orbital lobes will come here, okay, and T to G orbital lobes will come here, but the ligand is here. EG orbital lobe will come exactly at the center of the face of the cube, whereas T to G orbital lobes will come exactly at the center of the edge of the cube. So both are away from the ligand direction. Ligand is going in this direction, but T2G lobes are here and EG lobes are here. Okay, so that means both T2G and EG orbitals are away from the direction of the ligand. Now the question comes, which orbital energy increases more when compared to other one? In order to know that one, which orbital is more nearer to the center ligand direction, that we have to find out. That can be done by the angle measurement study. Here from the angle measurement study, it is very clear that the angle between the EG orbital, center metal ion and ligand is half of the tetrahedral angle, that is 109 degree 28 minutes divided by 2, that means 54 degree 44 minutes. So that is 54 degree 44 minutes. So that means if you consider the EG orbital lobes here, EG orbital lobes are exactly coming here. So the angle between this lobe and the center metal ion, which is exactly at the center of the cube, and this ligand, so that is exactly 54 degree 44 minutes. For example, if you consider here, if this is the ligand and it is center metal ion and it is the lobe of the EG orbital, now you have to consider the angle of this one. So this angle is 54 degree 44 minutes. Similarly, the angle between the T2G orbital lobe and center metal ion and the ligand is 1/3 of the tetrahedral angle, that is 109 degree 28 minutes divided by 3, that will come 35 degree 16 minutes. That means we know already the T2G orbital lobes will come exactly at the center of the edge of the cube. The angle between this T2G orbital lobe and center metal ion and ligand. So that means if it is a edge of the cube, if it is a T2G orbital lobe here, if it is T2G orbital lobe, okay, and if it is a ligand and if it is a metal. So what is the angle here? So this is around 35 degree 16 minutes. So that means the angle between the T2G orbital lobe and central metal ion and ligand is 35 degree 16 minutes. So now by comparing the angle between these d orbital lobes, that is T2G orbital lobe, central metal ion and ligand, and EG orbital lobe, central metal ion and ligand, it is very clear that the T2G orbital lobes are more nearer to the center ligand direction when compared to EG orbital. So that means from the angle measurement study, it is very clear that the T2G orbitals, that means T2G orbitals are more nearer to the ligand when compared to the EG orbital. So therefore T2G orbital will experience more repulsion when compared to EG orbital, okay, because EG orbitals are little bit more away from the ligand when compared to T2G orbital. That means T2G orbitals are more nearer to ligand field when compared to EG orbital. Therefore T2G orbital will experience more repulsion, hence T2G orbital energy increases more when compared to EG orbital. Therefore in a tetrahedral complex, which will not produce the spherical field around the center metal ion, so that means the 5D generated d orbitals will not experience spherical field in case of tetrahedral field. Therefore in presence of 4 ligands around the center metal ion in a tetrahedral fashion, the crystal field splitting is going, the 5D orbitals are going to split into 2 sets of orbital. That means T2G and EG orbital. Here in this case, EG orbital energy is more when compared to here T2G orbital energy is more when compared to EG orbital, because T2G orbitals are more nearer to the ligand field when compared to EG orbital. Thus, in case of tetrahedral complexes, the T2G orbital energy increases more when compared to EG orbital, which is exactly opposite to the octahedral field, where T2G orbital energy is less when compared to EG orbital. But in case of tetrahedral complex, what will happen? T2G orbitals are more nearer to the ligand field when compared to EG orbital. Therefore T2G orbital energy increases more when compared to EG orbital. Therefore by considering the average energy of the 5D orbitals in a spherical field or average energy of the average energy of metal ion in a spherical field as a 0, that is barycenter, the crystal field splitting in case of tetrahedral field, tetrahedral field or tetrahedral complex can be represented as shown in this figure 2. This one is figure 1 and this one is figure 2. So that means by considering the average energy of the metal ion in a spherical field as a 0, that is barycenter, the crystal field splitting in case of tetrahedral complexes can be represented in this fashion. So that means the splitting of d orbitals will looks like this one. Here one thing we have to remember is that here we are not going to represent Eg orbital as Ez. So that means we are not going to write G here, because tetrahedral complexes are not having center of symmetry. Okay. Similarly, T2G orbitals are represented as only T2, not T2Z. Okay, only T2 we are going to represent here. Okay. Now from the structure, crystal field splitting structure, it is very clear that the T2 orbitals are 0.4 delta T above the barycenter, whereas Eg, that means Eg orbitals are minus 0.6 delta T below the barycenter. Here the total crystal field splitting in case of tetrahedral complex is represented by delta T, where T represents the tetrahedral. That is, the magnitude of crystal field splitting is denoted by delta T, okay, where T stands for tetrahedral. Here the T2G orbitals are 0.4 delta T above the barycenter, whereas Eg orbitals are 0.6 delta T below the barycenter. Further, each electron entering into Eg orbital, that is E orbital, will stabilize the complex by 0.6 delta T per electron. That means 6 delta T per electron, whereas each electron entering into T2 orbital will destabilize the complex by 0.4 delta T per electron. Okay. Here it should be noted that the crystal field splitting in case of tetrahedral, that is delta T, is always less than delta naught. That means crystal field splitting in case of octahedral complex, and it is approximately, or it is exactly is equal to 4/9 of delta naught. That means the crystal field splitting in case of tetrahedral complex is always less than that produced in case of octahedral. Why it is that one? Why it will happen like this? We will discuss in the next video. Okay. So thus, crystal fields theory with reference to tetrahedral complexes, we have to explain how the ligand field will affect the center metal ion, that means degeneration of the center metal ion. So how will you explain that one? So in a tetrahedral complex, the metal will be at the center of the cube, whereas 4 ligands are occupying at the alternate corners of the cube as shown in this figure 1. Further, the direction of x, y, z axis are facing exactly at the center of the face of the cube. Okay. Therefore, the T2G orbital lobes are exactly pointing towards the center of the edge of the cube, whereas Eg orbital lobes are exactly pointing towards the center of the cube. So therefore, from the angle measurement study, it is very clear that T2G orbital lobes are more nearer to the ligand field when compared to Eg orbital lobe. Therefore, T2G orbital experience more repulsion when compared to Eg orbital. Therefore, T2G orbital energy increases when compared to Eg orbital. Therefore, by considering the average energy of the metal ion in a spherical field as a 0, that is barycenter, the crystal field splitting in case of tetrahedral complex can be depicted or can be represented in this as shown in this figure. Here the crystal field splitting, that means the magnitude of crystal field splitting in case of tetrahedral complex can be represented as, or it is denoted by delta T, where T stands for tetrahedral, and here the T2 orbitals are 0.4 delta T above the barycenter, whereas Eg orbitals are minus 0.6 delta T below the barycenter. That means each electron entering E orbital will stabilize the complex by 0.6 delta T, whereas each electron entering into T2 orbital will destabilize the complex by 0.4 delta T. Further, it should be noted that always the crystal pill splitting in case of tetrahedral complexes is less than the crystal pill produced in case of octahedral complex. That means delta T is equal to 4/9 of delta naught. Here minus sign indicates the reverse order of splitting in tetrahedral. So that means delta T is equal to minus 4/9 delta naught. And we will discuss about this factor in the next video. Thank you.